Okay, so let's start the morning session, the first talk. The first speaker is Aba Mbirika. He's going to talk about a co-Fi module structure of spring representations.
Okay. Thank the organizers for inviting me to come to Fields Institute. This is my second time here, but my first time speaking. Last time I was here, I was a grad student, not even in this area of math, and I erroneously thought that I was going to be a p-adic representation theorist. So, how did I get involved in this? Well, my PhD advisor decided that he was going to get a bigger and better and more awesome job, but he didn't tell his PhD students because it wasn't certain. So there I was, getting and going, and he's like, see ya. You can come to Nebraska with me, but why would I want to go to Nebraska? I was in Iowa. You know? Who ever want to move to Nebraska when they live in Iowa? So I said see ya, and then went to MSRI to search for a new world, and then a new professor at University of Iowa wrote me an email. I don't even think I had met her yet. Her name was Mbirika-Tymoczko, and she said, I heard you've been dumb. Oh, I know. She probably didn't say it that way, but she said, one of her first words was Spec-module. And I was like, what's that? And then my life transformed ever since. Yeah. So that leads me here today, and in this Hessenberg variety thing. Shout out to my friends coming there. Chris and Tasha from the band When Particles Collide. I saw their gig. They gave mathematicians a shout out. So I'm going to give a shout out. This talk would have been titled Representation Stability, but the reason why spring representations exhibit this phenomenon of representation stability is mostly because of this co-Fi module structure in the sense of Church-Ellenberg-Farb, who developed this concept in 2012. So I really think that this is the true title of the talk, and so anyone who studies these things knows where that leads. Representation stability. So let's start the talk. There's 6 parts of the talk. We're never going to see this. This is the post-talk slides. I don't know if you read that. But that's just in case I get some question I can't answer. I feel like it might be on one of those. But those aren't really relevant to the talk. But I have a feeling you might ask something that's on there. So 5 parts of the talk. Let's start with the motivation. And homological stability is one of the motivations for representation stability. So say we have a sequence of groups or topological spaces equipped with some maps, for example, inclusions, so that we have x1 into x2 into x3, etc., of topological spaces. The sequence satisfies homological stability if for each I there exists a positive n, so that the map induced on homology of the topological spaces here is an isomorphism whenever n is sufficiently large. So this might be a concept that we understand, or that we've seen before. In other words, the homology groups here, they stabilize after a certain point, and even though as the x of n changes, as n increases, these changes don't affect the ith homology groups. So this is kind of the essence behind what Church-Ellenberg-Farb did with representation stability. So what are some examples of spaces or groups that satisfy this? Well, it's pretty ubiquitous. We have the symmetric group. They satisfy homological stability. Grade groups, SLNZ, to name a few, automorphisms of free group of Fn here. So numerous other places where this thing shows up. So what is representation stability? So Church-Ellenberg and Farb in 2012 defined this to mimic the preceding definition that we have in the following way. I'm going to give an informal definition. So let's say we have a sequence of Sn representations. So we have some Sn modules equipped with linear injections phi sub I, so that we have phi1 into phi2 into phi3, etc. Then this sequence satisfies representation stability if there exists a positive n, so we're still in the same mode with homological stability, but this is where we change. So that if we decompose this Sn representation into irreducible symmetric group representations as such, then the multiplicities C lambda n are independent of n for n sufficiently large. So we have a decomposition after a certain point of an Sn representation where the multiplicities here are independent of some n here. So this b lambda n are the other, the decomposition into irreducibles. So some of you might be thinking, well, as n increases, the actual symmetric group representations are different. How can different things be stabilized, and how can the c lambda n stay constant? Well, we're looking at like named representations. For instance, like the trivial representation is the trivial representation of dimension 10, dimension 100, dimension 1000. It's still the trivial representation. The standard representation is the same. Take a Young diagram, you just pad the first row of the Young diagram. You always get the standard representation no matter what the dimension. So this does make sense. These things are like called padded partitions, and we'll see that in the after talk slides if you wanted to see a little bit more on that. But it's not very super important for the bulk of this talk. Yep.
Is what you're saying that like you're going to be that when you have the p parentheses lambda, that actually can be a say where you're going to actually make a rule about how you are padding a partition and increasing the number of boxes with some specific.
Yes. Yes. And sometimes we're padding, say, an empty partition to get a row, for instance.
You always pad the first row.
First row, yes.
That's the rule.
Mm-hmm. And so yeah. So let's see some examples of sequences of Sn representations where this type of stability holds. So if you read Church-Ellenberg-Farb papers, most of them and their students and others talk about the configuration space of n disjoint ordered points, this cohomology group where M is a connected oriented manifold. So this space exhibits representation stability. This is one that will come up in this talk, the R-diagonal coinvariant algebra on R sets of n variables. One, a cohomology of the moduli space of n-pointed genus G greater than 2 curves. So, and numerous other symmetric group representations. Since their work in 2012, a lot of them and their students and others have found more and more spaces to add to this. And our goal, Tymoczko and I, is to add one more thing to this called Springer representations. So our motivation is really, when R equals 1, we're looking at the classical diagonal coinvariant algebra, and we're like one set of n variables. So that's our next example. Let K be a field of characteristic 0, fixed positive integer n. Let I sub n be the ideal in this polynomial ring generated by symmetric functions with vanishing constant terms. So we've seen this already before. This is generated by the elementary symmetric functions of degree I. And the classical coinvariant algebra we're going to denote R of n is this quotient, polynomial ring, modulo the ring of symmetric functions, the ideal of symmetric functions. So this sequence is a graded co-Fi algebra of finite type. This is italicized because I haven't told you what this means yet. So, and I'm not going to yet. In the sense of Church-Ellenberg-Farb, and hence, this is representation stable. So, actually, what I mean by representation stable, I mean this is a graded ring. Each of the graded parts are representation stable. And I'm going to get definitely into that in a lot of detail. So, just want to throw the words out here that here's our first example. So Borel showed that this classical coinvariant algebra is isomorphic to the cohomology ring of the flag variety as an Sn representation. That's important because in this next slide we see here that this cohomology ring of flag variety is a very particular sequence of Springer representations. The Springer representation, namely when given when, well, we're going to see this too, so I'll define it when we're looking at the Springer variety associated to a column diagram. So, and the proceeding revealed that this particular sequence of Springer representations is representation stable. So in red, boom, does this hold for all representations? I knew that'd be red because I wrote these slides. Boom. So there's a hope for all of them. And the answer, and work in progress, I must stress, with Mbirika-Tymoczko, the answer is yes. And in this talk we sketch in dark blue because I think there's a lot of details to tell you why this sequence of string representations cohomology is a co-Fi algebra of finite type. Yes?
So can I ask a knowing question?
Sure.
So it seems like a beautiful concept. I haven't really looked at it before, reproducibility. Can you give those of us who haven't thought about reproducibility some clue as to what does the fact that string representations are stable in the sense, what would that tell us about string representations that we would have wanted to know before we thought about stability?
Well, one of the super nice consequences of it can help us answer questions about the cohomology ring that are guaranteed to have an answer. It won't tell us the answer, but it tells us questions such as how did the dimensions of the cohomology groups grow after a certain point? Does it grow pretty fast, slow, or is it polynomial in dimension? Polynomiality of dimension of both the characters and the dimensions of the cohomology group is guaranteed to exist if it's uniformly representation stable. So if you don't already know that something is representation stable, you may not go try to find that needle in the haystack of this formula. That there is a polynomial formula in the variable n as n grows for the dimensions of these cohomology groups or for the characters of these particular irreducible representations. So it kind of gives, well, it gave us in particular a reason to hunt down. A lot of the stuff that's not going to be in this talk is us trying to find polynomial dimension formulas for these things that we know it exists now because it's uniformly representation stable. So this is one of the byproducts. Let's try to find this. It gave us like sort of the confidence to say, well, this exists. So that's one of the outputs, one of the good reasons. I know there's more, and I don't know any other reasons why people are looking at this. But to be honest, I'm going to add.
Yeah, I was just going to, from like the geometric point of view, like just like with homological stability, one of the nice things about it is as you're calculating homology ring, you could focus on smaller examples. So something like projective spaces are homologically stable, and thus when you're computing their homology, you can deal with all of the smaller homology groups with an early calculation, and then just worry about figuring out what gets added in each step. Okay. As increase, and similarly, you have that kind of stabilizing feature here.
Okay, so if I understand correctly, what you're telling, the result is sort of a meta theorem. It sort of gives you a framework within which to attack other problems that you're interested in. Okay? Mm-hmm. As in, it tells you certain things about how you might deal with other.
If you are computationally inclined, then it is a meta theorem and a starting point. For some people, I think it's.
Well, so, I don't teach it imply it's not a result.
I think it's cool in its own right.
What?
Of
course. I'm sorry.
Cool in its own right.
Of course. I don't mean to. But somehow the feeling of it sort of as a message to the rest of us. Okay. Cool.
I think it's very cool that string representations actually exhibit this phenomena. And it's surprising, actually. Well, we'll see, because we're looking at any sequence of string representations, and there's a lot of paths through a Young lattice. And any path through the Young lattice, this will hold for. And that's surprising, because all we had going beforehand is one single path, one really special path, the flag variety, the column path. That particular path exhibited representation stability. But what was surprising is that this is pretty wild, that any particular sequence of growing, well, this will make sense as I say I define string representation and the sequence of them as they grow, and it kind of not the ideal. Let me talk more about that.
Sorry, in your stability sequence, the B's in your sequence,
mm-hmm.
do they all have to be?
They're all Springer representations.
Do they all have to be finite-dimensional? Or can they be infinite?
Yes, they will be.
They have to be?
It turns out in this case, yes, they will be.
But just in general for the
if they're going to be uniformly representation stable, yes, they will be finite-dimensional. Mm-hmm. Yeah. Okay. Well, So this is our big question. So let's answer this. We need some Springer theory. First to get us all on the same boat. So I had to throw this slide in here because this is a workshop on Hessenberg varieties, and a Springer variety is a particular type. So we know this definition. We've got the H vector. H of I is bounded between I and n. It's a weakly increasing sequence of numbers in this n tuple, or tuple. A flag, I'm going to use this definition. Set of all possible flags will be math frac F, and I'll use V bullet for our flag. Sorry, I'm speaking tech here, but math frac, bullet, I guess I can say dot, dark dot, but these underscore slash bullet will be our slash cut, recut. Okay, Martha. Okay, Hessenberg variety. Let's have an nilpotent operator, and then by matrices, the Hessenberg variety associated to n, and the function h is given by this symbol, and it's all the flags that where n sends vi into the h of I vector space. This is a fact that no one did say, but we all know this fact in this room, but I thought I'd say it. For any g and gln, if we conjugate our nilpotent operator, the Hessenberg variety corresponding to that conjugated nilpotent operator is homeomorphic to the Hessenberg variety associated to the nilpotent operator itself, so we may assume that n is in Jordan canonical form with weakly decreasing block sizes, blah. So the upshot of that is that there's a one-to-one correspondence between the Young diagrams and Hessenberg varieties corresponding to each conjugacy class. So we can use the n, or we can just use the shape, because now we know that we really just care about the Jordan canonical form of some given n. So that's why I put this little block here, because I want to have my Springer variety associated just to a lambda. Oh, I didn't tell you what Springer variety is. Maybe that should have been on the slide before this. Oh, it couldn't be because I was here. Springer variety, what is that? Well, we have two extremal Hessenberg functions. Tatsuya, you spoke, and you had the same slide, but your extremal was, you had this one, and he said that, true, this is a flag variety. Clearly, if everything gets sent into the space Cn, but then your lower one was Peterson. You're a lower. My lowest one is Springer. I was like, what is extremo? When you spoke, I was like, extreme? And then you had extreme too, but it was like Hessenberg. I'm sorry, it was nilpotent, semi-simple. Okay, so mine are all nilpotent. So this is the third version of this slide that you've seen, and they're all different extremal things. So when h is as small as possible, then we're looking at nilpotent operators, that's flag sets where the nilpotent operator takes vi into itself, or where flags that get stabilized by n. That is the well-known, celebrated Springer variety corresponding to lambda, and we denote it SPR sub lambda. So this is our definition for our Springer variety. So the Springer representation, what's that? It arises when the symmetric group acts on the cohomology of this family of varieties. So, celebrated theorem in 1976, Springer said given a partition lambda, the cohomology ring of this Springer variety carries a symmetric group action. In particular, this particular top degree homology group of the Springer variety is, well, it's an SN module. This is the irreducible SN representation corresponding to lambda. So this is the celebrated result. You have a very deep and geometric proof for this. Martha understands inside out. No? Okay. But it is like, whoa, to some people. And they're like, is there a nice way to see the action of the symmetric group on this cohomology group? So there's a nice little history on this. A brief history is 1981, De Contini and Pertesi made this more accessible as a quotient of polynomial ring, modulo an ideal. Here, Tanisaki looked at their ideal and said, oh, I can simplify that. And he simplified it by making math cal into just that. This is not a joke, by the way. This is the standard symbol. So, but if you don't read the paper carefully, you'll be like, yeah, that does look more simple. It is. But this ideal is generated by elementary symmetric functions. Partially, they're all symmetric within the variables present in each particular function that they're not. If I remove that word, then I'm lying, technically. So, but in 1982, Garcia-Perchesi gave a nice basis V lambda for this presentation. That was eased thanks to the Tanisaki simplification of the de Concini-Perchesi ideal. And then 7 years later, Weyman conjectures a minimal generating set for I lambda. And then it took 9 years later before Biagioli, Faridi, Rosas provided counterexample to the Weyman conjectures. So why do I care about that? Well, looking at their paper, they provided a reduced generating set for I lambda, and this set was useful in my thesis and further work, and particularly in this talk.
Sorry, what's the difference between minimal and reduced?
Well, we don't know. No one knows the minimal generating set for the Tanisaki ideals. It's still conjectured that there is one, but this is smaller than the number of generators that.
Just in a non-technical sense.
It's
Yeah.
smaller.
He just meant
This is
smaller
smaller
than what was
Yeah.
previously.
Yeah.
It's in a non-mathematical
There's
use of the
the
word.
Tanisaki ideal compared to the BFR generators. This is over. What's the word? There's some unnecessary generators here.
Okay.
So they gave a nice procedure, which I'll show you actually shortly in this talk, of how to produce the Tanisaki ideal with minimal hassle. Okay, so to define the Tanisaki ideal, we first have to establish a definition of these not quite so symmetric, elementary symmetric functions. So we want to talk about E sub d of S, d denoting degree. I'm just looking at d of the variables in this set of n, and we're looking at the sum of all those monomials. So this is a particular partially symmetric function. Here we have a set of elementary symmetric functions, EIS. So this has 3 parameters. The bottom left is the degree. Bottom right is the number of elements in this group of supersubscript of n variables. So this is going to be the set where we look at all the possible subsets of these variables, subsets that have size j. So an example is better than that. So let's give an example. Say we have n equals 5, we have 5 variables. I want to pick a subset of size 3. How about these 3? x1, 3, and 4. So if I look at the degree 2 monomials in this set, I've got this. This is definitely not symmetric. If I hit it with the transition 4, 5, boom, I jump out of this thing. But if I hit it with the transition 1, 3, cool. Everybody's happy. It's symmetric with respect to the elements in S. And so in that way, it's an elementary partially symmetric function. So if I let S, however, run over all 5 choose 3, or 10, there's 10 subsets of this of size 3, and then I add that to the set, that's what this E sub 2, 3 superscript 5 is. Now this set is definitely invariant under an SN action. This set, because if I have a transition 4, 5, well, this will jump out, but there's going to be one of these 10 different E sub 2 S's will have the one that says x3, x5, if I have the transition 4, 5 like this. It's somewhere in this set of 10 monomials. They're all going to structurally look like this, but with varying subscripts. So this was the essence of Tanisaki's idea in his ideal. Yes. To have, because we wanted the ideal to be invariant under the action of the symmetric group. Because we want an action on the quotient. Okay, so to avoid a cumbersome technical definition, we're going to explain how we get these generators, which I'm going to call G of lambda, for the Tanisaki ideal. So let's say we have this partition. there is a Tanisaki ideal corresponding to this partition of 9 boxes. So we number from the top left 9 until we run out of boxes and descend. Then after that, I know we have the numbers 1 through 5 yet. We have 5 boxes. How to handle them? Let's just go up like that until we're done. So, hence we get the generating set G lambda, which is blah. So where does blah come from? Well, we have 4 different sets of sets here. This one corresponds to the first column. This one corresponds to the second column, third column, fourth column. So what we get here is we have the bottom left number is the numbers in the boxes, 1, 2, 3, 4. So these are the degrees, and I want to take 9 of the variables from the 9 variables. Here in the second column, I want degree 4, 1, degree 5, 1, and degree 8, 1, and I want to take 8 of the variables from the 9 variables. So the numbers on the right are just the 9, 8, 7, 6. So this tells us the number of variables that we want from the 9 variables. This tells us the degree that we want of those 9 variables in the 9 variables for the first column, for instance. And that's it. Does that make sense? What's neat is to take a look at this one. So we're looking at the set of degree 9 variables where I choose 9 of the 9 variables. If I'm choosing 9 of 9, that's all of them. So for instance, if I need a degree 9 variable in 9 variables, well that is just E999. So a degree 9 variable, a degree 9 monomial, choosing 9 of the 9. Well, this is just E9, elementary symmetric function, which is x1, x2, x9. That's all that is. And this bottom one here, for instance, E1, 9, 9. I'm looking for total degree 1 monomials using 9 of the 9 variables. This is just E1. So the elementary symmetric functions will always appear in a Tanisaki ideal. And that was known, but in fact Tanisaki had all of them in all of his ideals. But the reduced generating set said, no, we don't need all 9 elementary symmetric functions. In fact, we can just take these 3, that's enough. And in fact, some sort of linear combination of these things will give all the missing ones in his ideal. So this is the nice reduction that Biagio Faridi Moses invented. So this will come up later in the talk. But there's a lot of slides between here and when, so it's memorize this. This is going to come up so much later in the talk, but I just needed to put it here. Made a choice. Okay. So, in particular, what I said, the far left column contains the elementary symmetric functions. So, yay. If you get anything out of stock, you can now build your Tanisaki ideal when you leave today. This is all good. Always a good thing to be able to do. Okay, so the theorem 2008, given lambda partition of n, Tanisaki ideal is generated by their reduced generating set. Yay. Okay, moving on. From now on, we're going to take this long polynomial ring word and just call it Rn. From now on. Every time you see Rn, I mean that. So, in 1982, they took the Garcia-Porchesi actually established this isomorphism between this particular polynomial quotient ring and the Springer variety as graded Sn representations. Okay, so this is a dog. This dog will reappear later in the talk. What are we doing next? Says the dog. So we now know what Springer representations are. Yep. Many slides ago, we said that this sequence of the cohomology ring of the fiber variety is representation stable. And moreover, this particular cohomology ring is a particular Springer representation which arises when lambda is the column partition. And we can see that if we want to test our ability to remember how to do the filling of to get the Tanisaki ideal generators, we put the 9 here. Sorry, let's be real. Let's say it's 9 boxes. So we go across, oh, that's it. And then we go to the bottom and we start numbering up. And then we looked at, we only really have e sub I 9, 9. So we just have the elementary symmetric functions. So I know that the Tanisaki ideal corresponding to lambda is just the e sub I. Or you can just say, oh, you're being silly. We already know that the Hessenberg variety associated to the nilpotent matrix that's n by n in Jordan. That has n Jordan blocks that are all size 1, 0 matrix. So we already know this for two different reasons why this is the cohomology of the flag variety. So the crux of the proof that this cohomology is representation stable is to show that this particular sequence is a co-Fi algebra of finite type. So it's time for me to say what co-Fi algebra of finite type means. So Fi and co-Fi. So in this talk we're going to give, there's a lot of information to give, but we're going to give just enough to prove our results, and then you'll go to the CEF, Church-Ellenberg-Farb, if you want to know more. So let K be a field of characteristics 0. So we're going to define bold n to be the numbers 1 through n. We're going to let Fi, or we're going to define Fi as a category whose objects are finite sets and whose morphisms are injections. So if you're seeing this for the first time, you can think of it in a different way. You can think of it as equivalent to the category whose objects are these finite sets. This is some very particular finite sets. And whose morphisms are injections from this possibly smaller set into this possibly larger set. So an Fi module, oh, by the way, this is me trying to define three different things at one time without saying the word respectively. So I'm defining Fi modules, I'm also defining Fi algebras, and the third thing I'm defining is graded Fi algebras. So an Fi module over K is a functor V from Fi to the category of modules over K. Simultaneously, an Fi algebra over K is a functor from V to K algebras. And lastly, what we're going to be looking at is Fi graded algebras, which are functors from the category Fi to the category of graded K algebras. I guess I didn't save any time because I said all that. I said that 3 times. Okay. Should have said it once. We're going to denote, so the functor takes this particular object to some one of these 3 other categories. We're going to denote that element that it takes to as this V sub n. So this will be a K module. This will be a K algebra or graded K algebra. Okay. So examples. So modules that carry this permutation action compatible with the permutation action on integers. This provides a rich source of examples for our Fi module, and the next is our most important for our purposes. And this example is the polynomial ring algebra. So we're going to define a functor R, where R sends the object n to this polynomial ring. So I've got this finite set, and I've got this algebra, this K algebra. I'm going to send, I have a morphism, which is an injection here. I'm going to send this to the homomorphism induced by the injection, which is F lower star. So that's going to send this polynomial ring in m variables to this polynomial ring in n variables, and will be a homomorphism. Induced by the condition that it's going to send x sub I to x sub whatever subscript that original injection sent that particular subscript. Make sense? So given that, that's it. This is a graded Fi algebra. By definition, there's nothing to prove here. This is it. We've showed it. In particular, Rn, the image of the finite set bold n under the functor R is just a polynomial ring. Kind of scares me to say all these category theory words, and I'm not really a category theory person. Yeah. The category co-Fi. So now that we've seen Fi, co-Fi is just the opposite category of Fi. In particular, the objects in co-Fi are finite sets They can be the same without less generality. We can call it the numbers 1 through n. And the morphisms in here are the same morphisms from here, except that we're now going from n down to n. So 3 things again I'm defining. I'll just talk about cofi module. Cofi module over k is a functor from cofi to the category of k modules. The same for those other objects. Or those other object choice of words. For those other things. So for instance, if V is a Fi module over K, then the vector space dual V star forms a cofi module. So a lot of the definitions that are just for Fi can be viewed as also for cofi. If I want to know, is this true for cofi, I just have to say, well, let's look at the dual of that. Does that satisfy the Fi-ness? So, okay. So, an example of a cofi module, well, it just so happens that the polynomial algebra, ring algebra, is an example of a cofi algebra. That's coincidental, but it's a really easy example, so I'm going to use the exact same example and prove why. So, we have a functor R, setting the object n to the polynomial ring, the same functor as before, but now remember, we're dealing with the cofi set. So the morphisms in the cofi are morphisms from n, the same Fi morphisms from little m to big N. But now we need to show that the map induced from this injection, it's not F lower star, it's F superstar, and it goes backwards, or from your perspective, backwards. Polynomial ring in possibly more variables down to this smaller ring, smaller polynomial ring. So how do we define this homomorphism? Well, it's going to take x sub I here to 0 if this x sub I was never imaged by the original f. So, and if x sub I, if the subscript I appeared in this image, if it came from somewhere, then we're going to send it to back where it came from. Does that make sense? Okay. So, having satisfied that, then R is a graded cofi algebra. Well, we can just say module, but I mean it's not a module, but it's an algebra because it has an algebra structure in the polynomial ring. Okay. So, finite generation, finite type. This is a super important concept. Many of the concepts from module theory carry over in this new setting. For example, we have submodules, quotient modules, etc. In particular, there's a very important notion of finite generation and finite type. So, an Fi module V is finitely generated if there's a finite set of S of elements in the disjoint union of the Vi, so that no proper sub-Fi module of V contains S. Ooh. An example is coming. And graded, this is more important. The graded F blocks, they're both very important. I don't want to say what's more important. But a graded Fi module is a finite type if each of the ith graded part is finitely generated for each I. Let me give an example of this. Because there's more slides to go in. I just want to give an example. We're going to see how this above definition differs from the corresponding one for modules over rings. Because these things incorporate an Sn action. So this whole idea of finite generation is as crystal clear, but I'm going to make an example that makes it crystal clear. And it's the same running example. This is a non-example. Polynomial rings here are not finitely generated as an Fi module. Indeed, it's not even finitely generated as a K vector space. We can't find a finite set of elements that can generate all of the possible monomials that come out of here, for instance. However, when graded by polynomial degree, each graded part of the sequence is finitely generated as an Fi module. So let's take degree 3, for instance, where we have monomials. I claim that these 3 generate all possible degree 3 monomials. Like, then you might say, well, how do you get x2 squared x3? How do I get x2 squared x3? Well, I hit this with the symmetric group action. I just take 1 to 2 and take 2 to 3, and boom, I got my x2 squared x3. I I got all the power functions here by just acting on this one. So this is sufficient. The Sn action actually has. So that's how we see that this finite generating set is kind of a sketchy thing here in this case, but actually we can really see what in degree D, it's generated it's finitely generated, the degree D part of this ring by these particular monomials. So we just need to say, well, how many ways can I get sums of numbers that add up to D? Sums of the exponents that add up to D. That's a nice combinatorics, cute little problem, right? Using stars and bars. Remember that, stars and bars. Of course, ours co-Fi algebra finite type. Also, because I was looking at Fi modules, but it's also a co-Fi module, so it has both the Fi and co-Fi structure. So this is super important to recall. This ring is a graded co-Fi algebra of finite type. Co-Fi algebra of finite type. That's very important for us to remember, and I will reiterate that. So an ideal. So we have these algebras, so we can talk about ideals. That are graded Fi algebra, if I is a submodule for which each object I sub n is an ideal in the particular algebra Rn, then I is called an Fi ideal, or co-Fi ideal. So these are submodules that have some extra algebra enriched properties of the multiplication. So now we can speak about quotients, since I have an algebra modulo an ideal, or an Fi ideal, or co-Fi ideal. This is defined so that the nth part is that, the nth element in the sequence. This is a sequence of spaces. This is the nth element in the sequence, which we can write as that quotient, respectively, for each n. So this is an Fi or co-Fi, depending on our situation. Okay, the definitions are slowly coming to an end. In this diagonal coinvariant algebra, so we have this setup of an Imaran. The ideals here do not form an Fi ideal since blah. Why did I write that? Because of reasons I'm going to talk about soon, anyways. If I have x1 plus x2, this is an elementary symmetric function in I2. Yep. So I have a inclusion map on the big space. So this better take if this was an Fi ideal, then this would be carried, x1 plus x2 would be carried into the next space. But this is not a symmetric function in the set of three variables. It's not. I mean, that's why I wrote blah. It was too long to fit there. However, they do form a co-F ideal. I can pick this out of I2 and I can go backwards and I can see it in there. I'm not going to give you an argument for that because we're going to do that in the Tanisaki setting, which is more difficult. So I can take a symmetric function in a bigger space and then I can send some variables down to set them to 0, and that will be symmetric in the smaller space. We've got some head nods, so you guys are seeing the proof, probably saying, oh, it's trivial. Not for the Tanisaki case. Okay, so so these are our two main tools. So it's not here yet. This is our first main tool. If we have a graded Fi algebra of finite type, and we have an Fi ideal, and all of these we can add code to this, then the quotient is a graded Fi algebra of finite type. And once we get a graded Fi algebra of finite type, we're very, very, very close to representation stability. So that's why this talk is titled Co-Fi module. Remember, algebras are also modules. So an Fi module over a field of characteristic 0, this is the most important theorem in the Church-Ellenberg-Farb. It associates a necessary sufficient condition for for representation stability, which is finite generation. If an Fi module over characteristic 0 is finitely generated, if and only if the sequence of Sn representations is uniformly representation stable, and each Vn is finite dimensional. That's the reason why we need that and have that there.
I'm sorry, have you told us what uniform, does that just mean the
It's
stabilization occurs? Oh, thank you.
It's a stronger sense, and it's on one of those talk about slides later. It just, I need to define a lot more stuff to say what uniform. It's just even better. Is that okay for now?
Yeah.
Yeah. Okay. Okay. So commit that to memory.
So you're going to show that it's finitely generated. Is that what you're going to
Yes, I'm going to show that each graded part is finitely generated. And but that's what's up here. If we remember from a bunch of slides ago, finite type means that each graded part is finitely generated.
Yeah.
So really what I'm showing, to show that this is a representation stable, I just need to show that each ith degree part is finitely generated. If that ith degree part is finitely generated, then that ith degree part of an co-Fi algebra is itself a co-Fi algebra in that degree, and it's a finitely generated co-Fi algebra, and I can use this theorem still, even though it says Fi, to show that that particular graded part is a consequence of it being finitely generated is that it's uniformly representation stable. So all we need to show is that in each of these graded parts, the Springer representation is finitely generated. And all we know so far is that the polynomial ring is finitely generated, but this quotient to be finitely generated, we need the I to be a co-Fi ideal. So now our new goal is to show that the Tanisaki ideals form a co-Fi ideal. And then we're winning. So let's bring that dog back again. Is this the same dog? No. Good. So anyone who doesn't recognize this being the same dog is not paying attention to the talk. You should be paying attention to talk and not worrying about which dog this is. It's fine. You'll pay attention from now on, right? More dog focused. This is a different dog. Okay. What's the same though? Okay, so recap. 4 slides ago, we said that this is a graded co-Fi algebra of finite type. Only 4 slides ago, way after the first talk. So I'm recapping exactly what I was listening to Megumi and I were just sort of having a conversation about. 3 slides ago, we said that we'll show that this sequence, the Tanisaki ideals, is a co-Fi ideal. 2 slides ago, we gave the proposition by CF, which allows us to conclude that our sequence of Springer representations is a graded co-Fi algebra of finite type. So what can we conclude about each ith graded part? I think I just said the answer, so I won't ask you again because you're dog focused. These are finitely generated. These are finitely generated. If I can just show that these are co-Fi ideal, because then this becomes a graded co-Fi algebra of finite type. The conclusion is these are finitely generated and then everything pops out. So this is the thing. I am going to show that, we are going to show that the Tanisaki ideals is a co-Fi ideal. So, Tanisaki ideal. Let's take a look at a sequence of Young diagrams such that lambda I has I boxes. For which sequences, if any, of Young diagrams does this corresponding sequence of Tanisaki ideals form an Fi ideal? So, myself and Tymoczko looked at this and said, and we built this up and found out that only the silly sequence forms. Well, I can say Fl-modu here because there's an algebra structure, so these would be, that's the same as saying ideal. So this is it. This is the only sequence that forms an Fi ideal. So we don't care about this. We want to look at every possible sequence. So this is not going to work. Let's try the co-Fi setting. For which sequences of any of Young diagrams does the corresponding sequence of Tanisaki ideals form a co-Fi ideal? Every single sequence works in the Young lattice, no matter how we travel through this growing add a box, and all the legal ways to create a Young diagram. So how do we show this? We need to show that so I'm recalling what a co-Fi algebra structure means. You have an injection from set of M to a possibly larger set. And this induces a map on the algebra, on the ring of algebras, polynomial ring, and it must preserve the Tanisaki ideal in this manner. That this one doesn't, for instance, in the Fi ideal setting for the symmetric functions. We need to take this larger Tanisaki ideal into this smaller Tanisaki ideal. I say larger in the sense that the diagram has got one more box. Okay, so we're going to show that. And so this is difficult to show because we have a ton of different possible injections. So we have to show this is true for every possible injection. So a sketch of what we did, I'm going to change the letters from R and I to A and J so that I can speak more generically. So if we have a graded co-Fi algebra and we have some Sn invariant ideals and each A sub n, then we showed that given an injection, and we have iota, an injection for, it will send I to I for all I in the little set M, then looking at F superstar of Jn is the same as looking at iota superstar. So forget all those injections. We've reduced this problem down to, let's just look at the special injection that sends the M things to their counterparts here. But then we simplified this even further. We said that if for each inclusion of this very special nature, where little m is now just 1 through n minus 1, to this set here, if the Jn gets sent into Jn minus 1 by this very particular inclusion map, then this set is a co-Fi ideal. So we reduced it twice. We've reduced it from all injections to just iota injections. We reduced all these iota injections into a very, very special iota injection. Okay. So now back to the specifics. We have our sequence of Tanisaki ideals. We just need to show that it sends this Tanisaki ideal into that via this very specialized iota map. So to do so, we prove the following combinatorial lemmas regarding the BFR generating sets of the Tanisaki ideals. We noticed or proved that iota sends this set. Remember, this is the degree. This is the subset of variables in the n variables in our. That beeping sound made me worried. Someone saying that I'm almost done.
Well, you have 9 minutes.
Okay. So we can decompose this into these two particular sets. If I went into detail on this, it would just be mumbo jumbo, blah, 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 blah. It's correct.
Wait, so I'm confused. What is lambda n and lambda n minus 1 here? What are those Young diagrams?
This is a sequence of Young diagrams. So remember when we have, I have a sequence of, I have a path in the lattice that's growing where there's lambda boxes here. This corresponds to a sequence of Tanisaki ideals.
Yeah, I'm sorry, but what are your lambda i's? What are they? As Young diagrams?
They're Young diagrams with I boxes.
Yes.
Any increasing sequence.
Which ones?
Any, which is what's great about this. We're not just talking about like columns. We're talking about any increasing sequence where we add a single box. So a possible increasing sequence would look like this. Any increasing sequence, and each of these correspond to a Tanisaki ideal, which also corresponds then to a particular.
Okay, I'm sorry. So the point
So
is,
I have this.
any old.
I have the sequence of Springer representations corresponding to these Young diagrams.
Okay.
I might write this small. So I have a sequence of Springer representations here, and I want to see if this particular sequence is uniformly representation stable. Well, the graded parts. So to look at a sequence of Springer representations, it just suffices to look at a sequence of what's the changing thing, lambda, the boxes, add a box, and the Springer representation grows. So I'm really just looking at a sequence of Springer representations that is kind of dictated by any random sequence of Young diagrams where we add a box. Because that's how we get from one Springer representation to the next size up. So these are in the big broad strokes that I've not really been writing when we're looking at a sequence of Sn representations here. Each of these Sn representations are, in this case, they're Springer representations, but they're represented by Tanisaki ideal here with one diagram. Polynomial ring in two variables. Modulo. Tanisaki ideal with two boxes. So this is some Springer representation. Some Springer representation, etc. Okay.
Can I ask, make sure I'm not confused? Sure. So what you're saying is, like, for instance, if I look at that 2-1 partition,
yeah.
So Springer's theorem says I should see the irreducible S21 at the top level in this quotient, right? And now your theorem says that
we should see that. Yes.
You should see like
the cohomology
Sn minus 1 at that level in the future guys.
Is that what?
So this says, I don't know, in dimension, whatever it is, the dimension of that Springer variety, I should see at the top dimension.
Yeah, the top cohomology is
this sec module S21.
Yes.
And then according to your theorem, if the stabilization started immediately, I would see at that level, not at the top level, S31, then S41, then S51.
You'd see a padding, I believe. Okay, well, I'm lying a little bit because there's some patterns where we add a layer on top of that too.
Oh, okay.
So I need to study this more.
Okay,
definitely.
But it's something like that,
yes.
but not exactly.
Yes,
that's great.
Okay. Okay. So there's this cool combinatorial thing. I can give you a really short reason why that works, but. These are some surprising combinatorial results. Like the Q-linear span of this set contains all the ones of bigger variables. These are all helpful in our proof. If we have this particular subset, or we have degree I partially symmetric functions in j variables, then we have the same degree I of j plus 1, j plus 2, j plus 3, all the way up to n. We can grow this thing. So all of these came in handy to show the one fact that Yoda superstar sub n preserves the Tanisaki ideal in the so-called smaller Tanisaki ideal. So now we know, well, if we believe that, and that we put it together to make some proof that worked, then we know that this forms a co-F ideal. So we have the following consequence. Boom. This quotient, sequence of quotients, which is the Springer representation, the sequence of Springer representations, is a graded co-Fi algebra of finite type. We have that because of after the second dog, we proved that all we need to do is show that this is a co-Fi ideal. Then since the Rn is a co-Fi algebra of finite type, if you quotient by any co-Fi ideal, the whole quotient becomes a co-Fi algebra of finite type. And finite type means that each graded part is finitely generated. If each graded part is finitely generated, we get... Oh, jeez. There's space here. I should have had the result. Okay. It's not there. I only practiced this once. I get a whole different section for what fits right there. Oh, no, it doesn't fit right there. It's rather long. Okay, so this is my last slide. The following are all true. Yes, this would never fit there. Okay, so each graded part of the sequence is uniformly representation stable. Yay! Consequence. For each k and each n, let pi sub kn be the character of the kth graded part of the Springer representation. This sequence of characters is eventually polynomial in the sense of Church-Ellenberg-Farb. We didn't look a lot at that yet. We've looked a lot at this. For each k and n, let dkn be the dimension as a C vector space of the kth graded part of the Springer representation. This sequence is eventually polynomial in the sense that there is an integer sk and polynomial pkn, so that for sufficiently large n, we know the exact dimensions of the kth graded parts. So we've got the Benny numbers down. And I can give you some formula. Actually, I have a whole wonderful page of stuff if I had more time of awesomeness. But this unpublished thing will come out at some point, and then you can see awesomeness. Thank you for coming to our first non-chalkboard talk. And if you want to know what's over here, scary things. You know, padded partition. See that padded partition thing is there, and this is the real definition of representation stable. That's like Kodak. That's scary. Should have had a dog there.
I have a question. Are any of the other cohomology rings that we've seen, or do you think, conjecture, are any of the other homology rings that we've seen possibly co-fi modules?
We've called that we've seen this week.
Yeah. Like I think the regular notebook probably isn't, but maybe some of the semi-simple.
That was my burning question when we were introducing ourselves, because I didn't even think of that question.
So you planted that in my head, and I don't even remember it.
No, that's really natural in this particular workshop on Hessenberg varieties.
Well, that's why I was asking about your about finite versus infinite. Like when you talk about the correct cohomology of regular semi-simple Hessenberg and just plug it into your theory, or
is what, because we have they're finite dimensional.
but
They'd still be
graded finite dimension. Yeah, graded finite type. So sure, you can plug it in and see what you're getting. Or at least you can ask the question. We're doing open questions this afternoon, anyway.
But how about in your new presentation, your presentation of the Peterson variety is that ring graded? I didn't notice within your sort of natural grading on the polynomials aren't homogeneous, are they? Or in your presentation of your
They sure are.
They sure are. So there's so this is a candidate.
Oh, it's a cohomology ring. That's great.
Yeah. Yeah. Sorry. Okay. Really being silly right now. But this is.
So.
I mean, so it's worth looking into the co-fi ideal structure on that
I
particular.
certainly am. Before we thank Aba again for a colorful talk, let's go outside and try to take group photos right after we thank Aba one more time.